Okay, welcome to the last lesson for Chapter 2. In Chapter 2, we're going to talk about the chain rule. So if you talk to anybody who's taken calculus before, they'll remember the chain rule. It can be a source of frustration for some people. You're going to find that it's very similar to the power of a function rule for you right now. And that's because most of the functions that we're dealing with right now are power functions or polynomial functions. When we move into further chapters and we look at different types of functions, we're just going to call it the chain rule. So in order to use the chain rule, we need to review something called composition of functions, which we learned about in advanced functions. So the composition of functions is basically when I put one function inside of the other. So if I'm given two functions, f at x and g at x, the composite function, f of g, is defined by f of g of x is equal to f with g of x subbed in for the x, right? So this is just saying replace all the x's in the f function with whatever the equation is for g at x. And we're going to take a look at an example here. So for our first example, f at x is x to the power 4, and g at x is just this line. And we're going to find the value of f of g of 4. So when I have f of g, it's just an open circle there between the g and it's in the midline. What this means is I'm actually going to sub 4, so I'm subbing 4 into the g equation, and then whatever that answer is, I'm going to sub that into the f equation. So the first thing I'm going to do is sub 4 in for the x in the g equation. I'm going to figure out what that answer is. So in there I've got 8 minus 5, so I've got 3. And now I'm going to take that answer 3 and sub it into the f equation. So I'm coming up here to the f equation and I'll put in 3. And so I get 81. In part B, we're going to do the same thing but in the opposite order. So it's g of f of 4. Over here we had the f first. So over here we were plugging 4 into g and then found that answer and plugged it into f. We're going to do it in the opposite order. What I want to know is, are they the same thing? Am I going to get the same answer? So this time I'm going to plug 4 into the f equation first. The f equation is x to the power of 4. So I get 4 to the power of 4. That's 256. And now I'm going to take 256 and plug it into the g function. So coming up here, I'll replace that x. And we can see right away, this is not going to equal 81 over like we had over here. So the order does matter. And when we type this all into our calculator, we'll get 507. So the order matters which one I put first. And remember, I'm always starting kind of at the back end of the equation and working my way through. So here I'm going to put x into the g function and then g into the f function. And we're going to just leave the x here. This time we don't have a number. So we're coming up with an equation for h at x. And it says, yeah, we're going to put x into g and then put that into f. So we can change it into this notation if that makes it easier. So g there. So I'm going to take the equation for g at x, that's 2x minus 5. And I'm going to plug it into the f equation. That means wherever I see an x in the f equation, I'm going to replace it with this whole expression in brackets. And so there's actually only one x in the f equation. I'm going to replace it with 2x minus 5. And that's my new equation for h at x. I'm going to leave it factored. In part D here, I want to find the derivative of h at x. So this is, remember, our power of a function rule, which is the same. The power of a function rule is a specific example of the chain rule. What it says to do is take the power on the outside, bring it out front, and make it a coefficient. Then leave the inner function alone and subtract 1 from the power. So that's just taking the derivative of that power. And then we'll multiply by the derivative of the inner function. So the inner function is the line, and the derivative of that is 2. So when I look at this, this here is really just the derivative of the original function g at x, right? If I went up here and found g prime at x, it would just be 2. And if I went up here and I found f prime at x, it would be 4x cubed. So this guy here is g prime at x. This guy kind of reminds me of f prime at x, except that they've replaced the x with the bracket. So this is f prime at x, but instead of putting an x in, they've subbed in 2x minus 5, which remember was our original g at x. So it's saying take the derivative of the outer function and leave the inner function inside of it, and then multiply by the derivative of the inner function. And that's the chain rule. That's going to work for us whether it's a power or not. And so it's written here, take the derivative of the outer function, leave the inner function inside, and then take the derivative of the inner function. And so here we're always thinking about this guy here is my outer function, and this guy here is my inner function. The way I learned this was talking about the outer function as the mama, or the mother function, and the inner function as the baby function. And so we were taught to differentiate the mother and leave the baby inside, and then differentiate the baby. So this would be here, the mama with the baby inside, differentiating the mother with the baby inside, and then this would be differentiating the baby. All right, in Leibniz notation, and this is one where I am going to ask you to use Leibniz notation in your homework, as well as that it's probably going to show up on the test. If y is a function of u and u is a function of x, then I think this is actually a simpler way to find the chain rule. If I want to find the derivative of y in terms of x, but remember y was given to me as a function of u, but I want the derivative in terms of x, then what I do is I take the derivative in terms of u. So it means that y is going to be given to me as like something with u's in it, right? So there'll be some stuff around it. I'll take the derivative in terms of u. So it's just kind of like normal, just a different equation, or sorry, a different variable. And then u is going to be given to me as a function of x. So I'm going to have some equation that says u equals some stuff with x's. I'm going to take the derivative of that, just like normal in terms of x. And all I have to do is multiply those two derivatives together. So it's nice and easy. And then in order to make it in terms of x, after I do that, I'll have to replace the u with the function of x. So we're going to take a look at what does that look like in an example when we get to example 2. The first thing we're going to do is just practice the regular chain rule. So the one that we've got up here, it says here to differentiate y equals the square root of 2x minus 1 with respect to x. So here, the outer function, or the mama function, is the square root, and the inner function is the line inside of it. So we're going to just take the derivative of the outer function, leave the inner inside. Sometimes it's nice to change that. Instead of writing it as a root, we write it as an exponent 1/2. And so when I take the derivative of this, I'm going to bring the 1/2 out front, leaving the baby, leaving the inner function in there, and subtract 1 from the exponent. So there I've taken the derivative of the outer function. I know how to take the derivative of a root. I'm always going to have that 1/2 coefficient and the negative 1/2 exponent. But I can't forget to multiply by the derivative of the inner function. So the inner function inside the brackets is 2x minus 1, and the derivative of that is 2. And then from here I'm going to try to simplify. So at the front here I've got 1 divided by 2, and at the end I'm multiplying by 2. So I've got multiplying by 2 and dividing by 2, that cancels out to 1. And I'm just left with this bracket here. Now the bracket has a negative exponent, so it's going to go to the bottom. So the only thing left on top is going to be the 1. And the 1/2 exponent tells me that it's a square root. And there I'm done. So in example 2, we're going to take a look. Oh, sorry, I lied. It's example 3. In example 2, we're going to find the equation of the tangent to the curve. So we've got this complicated expression here inside the brackets. The inner function here is a fraction. And that's our baby. And then the outer function is the power of 1/3. Okay, we're going to find the equation of the tangent. Remember, that tells me I need a point and the slope. And we wanted it x equals 9, so we're going to use that value for the point and for the slope. So I'm going to get started with the point. Doesn't matter, you could have done slope first. The point is just to plug the x value into the equation. So at x equals 9, so inside here I get 8 over 1, and I've got to the power of 1/3, which means to take the cube root of 8, which is 2. So I've got my point, 9 comma 2. Next we're going to find the slope. So for the slope, we have to take the derivative. This is a chain rule. We've got an outer function and an inner function. So first, taking the derivative of the outer function says to bring the 1/3 down, leave the baby inside, and subtract 1 from the exponent. Now we have to take the derivative of that inner function. But notice that that inner function is a quotient rule. So I'm thinking about, to find the derivative of the inner function, I'm going to use the quotient rule, which tells me to do u prime v minus uv prime all over v squared. So I'm just kind of thinking about that shorthand in the back of my head as I go through this. So taking the derivative of the numerator, that's my u, then I have 1 times the regular denominator. So we've done these first two. Then we're going to subtract. This time we're leaving the numerator alone. And we're going to take the derivative of the denominator. So now we're done. And then we're going to divide all of that by the old denominator squared. All right, so I'm going to clean that up a little bit. I am looking for the slope at a particular x value. So at any point I can pull a plug and sub in x equals 9. I think it's going to make my life a little bit easier to do a tiny bit of simplifying first. One thing I'm going to do is, for a negative exponent on a fraction, that tells me to just flip the fraction over, and I can make the exponent positive. And then the numerator here, I'm just multiplying this first bracket by 1, so it's just x minus 8, and then here I'm minus x and then plus 1 when I distribute that negative in. So when I collect like terms here, the x's actually cancel out, and I'm just left with negative 8 plus 1. So I've just got negative 7 actually on top, so that's quite a bit easier. All right, so now I'm going to sub in my value. And I'm doing just simple arithmetic when I plug this in. So I'm just doing the subtraction in the numerators and the denominators. When you're evaluating this one, don't forget that you can, when you have an exponent on a fraction, it goes to the numerator and to the denominator. So on top, 1 to the power 2/3 is just 1. And on the bottom, I'm going to have 8 to the power of 2/3, or you can change that into a root. The denominator of the exponent tells me the type of root, so it's the third root of 8 squared. And then we've just got negative 7 at the end. So the cube root of 8 is 2, and then I've got 2 squared, and so that's 4. And so all together here I've got negative 7 over 12. So that's our slope. This is our m tan. And we've got our point. We can now come up with the equation. So the equation of the tangent line is always y equals the slope number times x plus that mystery y-intercept. And to find that, I'm going to sub in my point. And then we'll do a bit of reducing here. I've got 9 over 12. That's the same as 3 over 4. You don't have to do it there. You can reduce the fraction later. And so what I get then is negative 21 over 4. I'm going to bring that over and add it on the other side. But when I add two fractions, instead of writing a 2 here, I want to have a common denominator. So it's going to be, instead of 2, it'll be the same as 8/4. And then I'll add those guys together, and I've got my v value. So depending on the question, if it just asks for the equation, you can give me the equation in y equals mx plus b form. If the question asks you for standard form, then you're going to multiply through by the lowest common denominator, which is 12 here. So I'm going to multiply each of these terms by 12. So 12 times y. And then when I multiply this one by 12, the 12s will cancel out and I'll just be left with negative 7x. And then when I multiply this one by 12, the 12 divided by 4 would give me a 3. So I'll be left with 29 times 3. And then I can simplify that is 87. But with standard form, I want to bring the x term over so that it's positive. So I'm going to add it over to the other side. And then instead of having 87 over here, I'm going to subtract it over to the other side. And then you can put, this question didn't specify, so you could be putting this in your sentence or this. All right. Next up, these two questions, you're gonna have to get a separate piece of paper to work through. So I've moved this one over here. In this one, this is where we're going to use that Leibniz notation. So if I wanted you to on the test, I'm going to tell you to use Leibniz notation, or I'll have this notation here, the dy by dx. And that's the rule that I want you to use. I'm going to do this one twice though. First, I'm going to use the regular chain rule that you're comfortable with, and then we're going to move on to the Leibniz to give that some practice. So we're given two equations here. One of them is in terms of u, and then I've got u in terms of x. Now I want to find y prime in terms of x. So in part A, the first thing it says to do is find y in terms of x. So I know that y is equal to u cubed, and I want to find it in terms of x. So what I'm going to do is just sub in u is equal to cube root of x. And I get y is equal to, the square root of x. So I get y is equal to the square root of x cubed. And then it says to find y prime. So before I find y prime, I am going to change this guy so it looks like an exponent. So I've got x to the 3/2. And then I can take the derivative. So the derivative tells me take the exponent out front and then subtract 1 from the exponent. And so I end up with 3 times the square root of x all over 2. In part B here, we're going to use the Leibniz rule. So I'm just going to rewrite it here so that we remember. The Leibniz rule is dy dx is equal to, just take the derivative of y in terms of the u and multiply it by the derivative of x, of u in terms of x. Okay, so all I have to do is go back to the original equation of y and take the derivative. It's got a u in it, just leave the u in it. So the derivative of u to the power of 3 is 3u squared. And then I'm going to multiply by, take the derivative of y, or u, that's a u, take the derivative of u in terms of x. And so we've got x, the square root of x, which is the same as x to the 1/2. You might need to write that down still if you haven't practiced it enough. And so to take that derivative, it's 1/2 x to the negative 1/2. And so now I've got my expression, but the statement does say I want to have y in terms of x. So I am going to sub in and get rid of the u. I don't want any u's, I only want it in terms of x. So I'm going to sub in that u is the square root of x. And so now I have, and I'm just going to simplify this second guy here. It's a negative exponent on x, so he moves down to the denominator. And the 1/2 exponent becomes the square root. All right, so all we have to do now is simplify this guy. I've got this square root of x squared. And so there's a couple things you could do. You could simplify that and then use your exponent laws from grade 9 and grade 10 and just subtract the exponents on the x's to simplify. Or because I've actually got them as both roots, I'm going to say that there's 2 of them up here and 1 of them down here, so they cancel. And so I'm left with 3 root x all over 2. So it's a similar amount of work, the 2 different methods. But what you're going to find is the more complicated these 2 functions get, the easier part B will get for you. Whereas over here you'd have to do a bit more simplifying and you might have a more complicated expression. So here when we simplified it came out really nicely to take the derivative. But if I have more complicated expressions, it won't simplify nicely and I'll end up with like an extra product rule or quotient rule, or still having another, like a more complicated chain rule, that kind of thing happening. Whereas over here, you're going to have 2 simpler functions to take the derivative of. All right, in example 4, we're taking the derivative at x equals 8 if the y function is in terms of u, it's a parabola, and then u is in terms of x. So again, I'm going to practice using my, it's asking me to find dy dx, so I am going to use my chain rule that says take the derivative of y in terms of u, and then just multiply it by the derivative of u in terms of x. All right, so just looking at the y function here, I'm going to take the derivative of this. We know how to do that, 4u minus 5, and then the derivative of the 3 is just 0. So I've got the first piece, now I just need to find the derivative of this second one, and I'm multiplying these 2 things, so I'm just going to use brackets for the multiplication. So bringing the 1/3 down, and then subtracting 1 from the exponent, and then the derivative of x is 1. All right, so we're almost there. We actually want to find the value of the derivative at a specific x value. So remember, whenever I have that specific x value, I can pull the plug at any point and plug in that number for x. You have a couple of choices here. You can replace the u with the expression in terms of x, and then plug in the value for 8. So I'm going to plug this in first and then this. Or you might plug the value of 8 into this expression, find that answer, and then plug that in here. It doesn't matter. Either way, you're doing 2 substitutions. Just to match what we did above, I'm going to sub in the u expression. And so I get and I'm going to simplify this as I go here just a little bit. I'm just moving that negative exponent down to the bottom and changing the fractional exponent. That's the cube root. Can you read it? I'll try and make it a little bit finer. The cube root of x squared minus 1. All right, so now that we've subbed that in, we can sub in our x value as well. So instead of saying sub in x equals 8, you could actually say at x equals 8, the derivative is and again, I just took that fractional exponent and changed it to a root. And now we just have to evaluate everything. Cube root of 8 is 2. And down here as well, the cube root of 8 is 2. And so we've got 4 times negative 6, that's negative 24. And here we've got 1 over 3 times 4, so 1 over 12. And in the fraction here, if I've got 1/12 and I'm subtracting 1, that's the same as subtracting 12/12. So I've got negative 11/12. And then if I multiply these two together, I get 319/12. And that is in lowest terms, so I'm all done. All right, that's the end of chapter 2. Enjoy your homework.